Mm. Mm. Good count.
Welcome, Mr. Mohit Verma.
Hello. Hello, sir. How are you, sir? Hello. Am I audible, sir?
Yes,
Hello. Thank you.
Bharmaji, you can check the screen to share. Mr. Verma, can you hear me?
Yeah, hello.
Yeah, Mr. Verma, can
I'm
you hear
sharing
me?
my screen only, sir. Yeah,
Yeah.
I'm
Check
sharing,
it,
sir.
check it. But it is not visible right now. Please check it.
Oh. Sir, is my screen visible now?
Yes, yes. Screen is visible now. Yes. Check whether your slides are sliding or not. Sometimes it happens. Next slide.
Yeah, last time it has happened. Let me check.
Next. Yeah. That is why you check the slides.
Let me check it on the full screen mode also. So, is it changing, sir?
Yes. You can do that because you have not yet started, na?
Okay. Yeah, it's better to check prior.
Yes.
Otherwise, on the spot,
Yes.
sometimes this computer system
Yes.
create
No,
an
it
issue also.
happens. It happens many times in our systems. That is why it is better to check it
Yeah.
out.
Switch on the lights. These things are visible to me. Kind of.
Uh, ready. Just I'm enjoy.
आ जाओ सर
Respected participants, we are start webinar because our advisor sir is busy in a meeting. He will join. Uh,
yeah, sir. Shall I start, sir, or we should wait
Mr.
for
Brahma, do you
the?
hear me?
Yeah, I can hear, sir. Hello.
No, wait. Just wait. Just wait for a minute.
Sir, your voice is breaking quite
Sure,
a
sure,
lot.
yes.
Hello.
Uh,
Sir, just let me change some internet. Just a second, sir. Yeah, just
there may be some.
it's a connectivity issue. Just give me 1 minute. Yeah, just 1 minute, sir.
Okay, no issue. No issue. कब क्यों हो रहा है?
Just give me 1 minute, actually. For sometimes it's the internet connectivity.
यहाँ मेरा क्या लिखा हुआ है?
Sir, is my voice better now?
Yes, sir.
Hello.
Your voice is good now. Your voice is good.
Yeah.
It's
So,
absolutely fine. Voice is absolutely fine.
and my screen is visible, sir?
I think there's.
Please make it full screen.
Yes, yes.
Yeah, I'm making it full screen only.
The
First,
screen is
let
quite
me
big.
check that whether it is.
Whether it's moving or
Good afternoon to all. First of all, I would like to thank SPM Nivas for giving me an opportunity to present my work. And basically, today, hello.
basically,
Yeah, sure, sir.
as well as Mr. Mohit Verma. Feeling proud to host the webinar. He was participating. On the topic, feasibility of nanofiltration for uranium removal from contaminated groundwater. Engineer Mohit Verma is a postgraduate engineer in soil mechanics and foundation engineering, currently pursuing PhD from IIT Ropar, Punjab. He is working as executive engineer in Punjab Water Supply and Sewerage Board, especially working in quality control laboratories, designing and planning of water supply and sewerage projects, low-cost innovations in drinking water mitigation, hydrogeochemistry, contaminant transport, wastewater remediation, sewage cleaning, and development of online IT-based modules for water quality sampling and distribution of sodium hypochlorite solutions. Perhaps you are aware that uranium is a chemical and radioactive toxic contaminant found in the groundwater of mostly in southwest region of India at level breaching the acceptable levels by the BIS of drinking water requirement. In this presentation, Engineer Verma has made an attempt to evaluate the potential of forward osmosis process on the removal of uranium from contaminated groundwater at low TTS scenario representative of field conditions. Further, effect of pH value in absorption of uranium in achieving World Health Organization's drinking water guideline value for uranium via forward osmosis process will also be discussed in this presentation. Really, this is a very high-level presentation which have great academic value also. And so I request all the participants to keep their microphone muted until the presentation is over. After the presentation, you will have time for a interactive session where you can ask some questions to Mr. Barma to clear your doubts. So it is my request to all to keep your microphone muted. And now I request Engineer Verma to give his presentation. Thank you.
Sir, first of all, thanks for giving a nice introduction about me. So, first of all, I would like to thank SPM Nivas to present my work. And basically, before I begin my presentation, let me tell you all that this is basically my PhD work that I have done at IIT Ropar. So, primarily, I work with the membrane technology for uranium removal. So, this is core work that I have done in my PhD. So what you are going to today, but I will not be taking it too technical or mathematicals, that side. So I will try to keep it generic. And prior to start, what I have done or we have done at IIT Ropar for this technology forward osmosis. First of all, I will be covering the basics about what is forward osmosis. After that, I will show what we have done for this technology. Secondly, this presentation will be more towards like the process side. So this is just a part of how at a lab level we work for mitigation technology. For a particular contaminant, say like uranium or selenium, arsenic, you can take any contaminant. But there is a scientific approach that has to be followed to develop a lab scale strategy to mitigate in lab scenario. Then later that technology can be scaled to the field or we have to do the first pilot. But the first step is we have to establish the whether the technology will be successful or not. That is through the laboratory experiment only. So today's presentation will be more towards the process side, how a laboratory based approach can be applied for mitigation of any contaminant. For this case, we have taken uranium, but this process can be adopted to arsenic, selenium, or any other contaminant also. So in this presentation, I will be covering basic, what are the terminologies, what is fundamental of osmosis, and how this technology is better than other technologies. Then what is basically draw solution that I will be covering in my next of presentations, and how basically the transport of contaminant occurs in the membrane, and what are the application of these technologies and limitation of these technologies. After that, I will be covering the how we have taken the problem of this Malwa region or this the pockets of Punjab which we have identified, and how we have implemented this to in the laboratory level. So first of all, why we have gone for this approach. So you might be aware of, I will not be spending much time on this slide, but in Punjab, as per CGWB report, this survey was done in 2020, and the major district for uranium hotspot have been identified in Bathinda, Barnala, Faridkot, Ludhiana, Muxar, and Moga. And the maximum concentration as per CGWB report has been found as 156 ppb, which is around more than 5 times of the WHO drinking water scenario. And the possible sources of uranium that, as per literature, exist in Punjab scenario is due to uranium mineralization, and that is of geogenic origin. So basically, I will be going directly to the membranes. So
So there is no voice. Mohit, there is no voice.
Voice, please.
Voice, please. Mohit, sir, your voice is breaking probably. There is no voice from your side.
the size of the molecule, it has quite many factors like charge screening.
Now, sir, your screen is wiped out from the. It is not there. Your presentation. Please reconnect. Please reconnect.
Yeah, let me reconnect it. Just a second. Yeah, this happened last time also. I don't know why this things, yeah, just this happens actually. Entire screen. Hello, sir. What is the scenario now, sir? Hello.
Yes, visible now.
Okay, visible.
Yes.
So I was telling about the basic of membrane. So how a membrane works, and
Sir, yes. Now, yes, start. Okay.
so based on the various size of particles, a membrane can be defined in the four classification. Like as you can see, microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So based on the size of what is the pore size of the membrane, we can define in these categories. So microfiltration can be used for suspended particles like the suspended solids, bacterias, whereas ultrafiltration membrane can be used for the macromolecules like organic matter, natural organic matter and all, and viruses also can be removed using ultrafiltration. Then comes the nanofiltration, which is in between of reverse osmosis and ultrafiltration. So how nanofiltration works primarily because it can remove multivalent ions. Multivalent ions means like the ions which have the more than monovalent charge, like calcium, magnesium, sulfates, that can be removed easily with the help of nanofiltration because the separation is prior to the charge. The charge plays quite important role. Size is secondary in nanofiltration. It can remove the smaller particles less than the size of the membrane, primarily due to the charge-based forces. Then the last one is the reverse osmosis. Basically, that is quite thick membrane where the pore size of membrane is so small that it allows only the water molecule to pass. It will not allow any ions like calcium, magnesium, sodium, potassium. Even the monovalent ions are not able to pass through the reverse osmosis. So that's why people say RO membrane can remove everything from the water because it will not allow any ion like calcium, like sodium, potassium, even chloride also. So monovalent species are also removed from the membrane. And how basically we optimize the membrane filtration or we select for the commercial angles what is the fundamental properties of membrane that we focus to design a system, that is permeability and selectivity. So first of all, let me tell you, permeability is the rate at which the water flux we can get. So larger the water we can get at a constant pressure from the membrane, higher is the permeability. So basically it's a rate of the water that is coming out of the membrane at a constant pressure, that is permeability. And selectivity is basically like the size of particle is in such a way that it will be allowing the smaller particles, and just above that size it will not allow. But practically speaking, the pores in the membranes are not like that. We get quite some distribution of pore. So practically speaking, a membrane is in between selective. So we call it selectivity permeability trade-off. If we try to achieve the selectivity to target a contaminant, then we have to compromise with the permeability. If we try to optimize with the permeability, then we have to make the compromise with the selectivity. So that is the way we have to go with the innovative approach in a membrane system. So to cover this trade-off mechanism of permeability and selectivity, that is a barrier basically. Second is mechanical strength, thermal strength, and chemical stability. So normally the membrane is made of the polymers. There are a number of materials in which we can go for a membrane, like ceramic membranes, like polymer membranes. Polymer membrane can be polyimide membrane, polyethylsulfone, cellulose triacetate also. So depending upon the every polymer have different mechanical strength, thermal properties also. Like a membrane can operate in a designed thermal temperature range. Otherwise, at higher temperature, the pore mechanism will change, and then the selectivity and permeability of membrane will change. Second is chemical stability. Like if we go for quite harsh chemicals like acids, or if we use for some industrial application like uh, tanneries and all, then we have to see the chemical stability of membrane because at harsh condition of acidic and basic side, the functional component of membrane that degrades. And third most important concept about the membrane system, that is fouling. Fouling is basically the deposition of the film or the contaminant on the membrane, due to which its flux reduces, its performance reduces. So that is called fouling. Fouling happens mainly due to organic matter and due to development of the microorganism on the membrane layer. That are the prime component due to which fouling arises in the membrane. And second is last is high operating pressure. Like RO and NF are diffusion based membrane, so we have to apply quite high pressures in RO and nanofiltration to make function ready. To get a good amount of flux through the membrane, we have to give quite some high amount of pressure. For your information, let me tell you, in RO membrane, we have to operate membrane at more than 20 bars. 20 to 60 bar is the range for the RO membrane. And for nanofiltration, we can go, the range is from 5 bar to 20 bar. That is the operational range for nanofiltration. And basically, for what is forward osmosis? Forward osmosis, as the name suggests, it is quite a basic technology. It's basically the primary osmosis. So reverse osmosis, it is simple osmosis in laymanish word. So how the forward osmosis works, so that I will be covering in the next slide. But prior to that, let me brief you some basic terminologies in the forward osmosis. So the feed water is basically that we use for the contaminant which has this is influent that we want to treat. That is basically the feed water. It can be a groundwater, it can be a leachate, it can be industrial water, it can be a wastewater. Based on the application, a feed water is basically which we want to treat. That is feed water. So the draw solution is basically a solution that is we use in forward osmosis, except feed water, that is used to draw extract the water from the feed water. So how basically forward osmosis works? It works on the principle of osmotic closure from the solution which is having low concentration, and where we have the high concentration of solutes, the solvent will pass. That I will show you in the next slide. And membrane is, we use a semi-permeable membrane. Basically, it's a dense non-porous membrane. Primarily, we can use polysulfone membrane also, polyimide membrane also, cellulose triacetate is also a popular membrane that can be used for forward osmosis membrane. Solute is a substance which is dissolved in water to maintain the osmotic pressure. So basically, to keep system running, to extract water, we have to add some solute in a draw solution. That is basically that we use. It can be a salt, it can be a glucose. Based on the application, it can be a nanoparticle. So basically, all that design of process is depending upon the draw solute only. Solute recovery. So basically, after we have finished the process, we have to recover the solute so that we can use for the next step. So this is basically fundamental concept of osmosis. How it works, let me tell you. So you look at this, the first cartoon, that we have a semi-permeable membrane in between, and we have a feed water where you can see less solute is present, and we have a brine. Brine is basically the draw solution here. So what will happen? Due to high osmotic pressure of brine, because it has quite high concentration as compared to feed, so the water will move from the left side to right side. So the volume of water will increase here. That is basically osmosis, how we can use, and this is a pressureless system. We need not to apply any pressure on the membrane to run the osmosis. So osmosis is a self-driven process. It is basically, the main driving force is concentration gradient. Higher the concentration gradient between draw solution and feed, more is the rate of filtration. So after that, let me show you the RO, how this RO typical system works. RO is a reverse system of forward osmosis. We have this high concentration on right hand side, and we apply a pressure through a force called delta P on the high concentration side. So due to this high pressure, the water will move from right hand side to the low side. That is basically the reverse osmosis. And what happens mainly, reverse osmosis need external pressure, whereas forward osmosis don't require the external pressure. As we don't have need to apply the external pressure, So the energy consumption for forward osmosis is less. Secondly, the membrane will be fouled less because we are not applying external pressure also. That is advantage of forward osmosis over the reverse osmosis. So this is the basic process how the forward osmosis works. So this is the basically we have this is the draw solution side, blue side. So where we have a saline water called brine that will flow constantly at a pressureless system. And here basically we have this the draw solution on this side. This will rotate and water will from this basically left hand side to move to the right hand side. And after we get because the draw solution that we have used will get diluted, and we have to regenerate the draw solution that we have to recover. For this we have to go for a recovery method that I will be covering in next slide. And after recovery we'll get the product water or final water that we can use for the commercial purpose or the drinking water use. So that is a process. It is a two-way process. First we have to extract the plain water or the pure water from the contaminated water to draw solution. Then from draw solution we have to separate out the solute to get a pure water. So it's a two-step process. Whereas in case of reverse osmosis, it is a single step approach. But overall, if we say the energy consumption or the membrane fouling or the performance is better. That's why this process is more advanced and the research are going in this the forward osmosis, where the reverse osmosis is already in market. So these are the some of the benefits of forward osmosis over the other membrane technology. Low fouling, because as we are not pushing the water through the through the membrane, so it will have the low fouling as compared to reverse osmosis. Second is we can go in high concentrations because the fouling is not there. The concentration polarization, that is basically one of the limitation factor in this reverse osmosis, that is not there. So we can achieve quite high concentrations in forward osmosis. So this is primarily used for the concentration process. Like I have a leachate or I have an industrial sludge, I can extract water to make a cake, the solid cake from the process without fouling a membrane, that which is not possible in case of RO. So we can extract water to a so high stage that it can become a cake. So that is the advantage of forward osmosis. The amount of rejection that we get, the membrane performance is quite better, quite high as compared to reverse osmosis. And we are operating without any hydraulic pressure. So this is a osmosis behaving process. So we did not need to have an external high pressure pump or the temperature losses. So that will that is free utilization of energy because of the we are having the osmotic pressure between the stream. So generally, what is draw solution? Draw solution can be a salt, like draw solution can be a glucose. Draw solution can be a magnetic nanoparticle. Now people are working on magnetic nanoparticle. Basically, what they will do, they make a magnetic nanoparticle that they will dissolve in water, and after they carry out the draw solution process, then they will turn on the magnet to separate out the magnetic nanoparticle out of water, and water they can use. So that is a advanced stage of draw solution that now these days the research is going on. Magnetic based nanoparticle for a draw solution. So fundamentally, how the draw solution, the suitability of draw solution depends on these 4 or 5 factors which I have listed here. First one is the concentration. Higher the concentration, higher is the osmotic pressure. That, as you can see from this the graph, higher is the concentration, the higher will be the osmotic pressure. And osmotic pressure is the reversible proportional to molecular size. For example, smaller is the size of molecule, higher it will be having the pi, the osmotic pressure. And charge and ionic strength. This is a software only stream that we use for the calculation of that. I will not be going into the detail, it will be too technical otherwise. And the research area that I have already explained you. So this is the transport mechanism, basically how the transport mechanism I will not be covering here because otherwise it will become quite uh, technical otherwise. So these slides I will be missing. After that, the application, how this technology is being implemented or what are the possible application of this forward osmosis technology. So it is developing. It is not really basically commercially available. People are doing quite some research on this technology. For example, there are company like Forward Water Technologies which are working on desalination. So from the seawater, they are extracting the fresh water through this technology that is emerging or advanced technology. And hydration technology, this company is working on emergency drink, like, so we use this glucose drinks and all. So you might be aware of the US Army has, they call it like the emergency bag. So what they use, they pack the hydrated drink or the solid glucose and some nutrients in a packet. In the packet, they just add a membrane of forward osmosis. In case of emergency, when there is no rescue or when you don't get the fresh water, the military person will, what will they do? They will take the muddy water or any water they will get from road or pond, dirtiest water they will take. Or sometimes some people I have, as per the literature or documentaries in the internet, or we have the literature, some people use your urine also. Like in the case of emergency, they put the urine in that bag, and through the osmotic pressure, only the water, pure water, that is extracted, and the drink, this hydrated drink, will be prepared automatically due to osmotic pressure. And that, in case of emergency, this US Army people can use. So that is one of the advanced technology that they are using for the defense sector also. The application of forward osmosis in defense. So one is brine concentration. Brine is basically high saline, high salt stream that can be concentrated further using the forward osmosis. Where if we go for traditional RO membrane or nanofiltration, then brine will not be able to concentrate because of the limitation of the normal membrane system. Then the next is osmotic power. Osmotic power, basically based on the gradient of this osmotic pressure, we can generate the energy. And the last application is desalination. So these are the basically the limitation of forward osmosis prior to starting my work. So low solvent flux, as compared to the pressure driven membranes, these membranes have the low flux, quite low flux. So to get sufficient amount of water, we need to have a large surface area of membrane packed in such a way that we can optimize for the amount of water. So the flux is low, so we have to see how we can have to provide the area of the membrane. That is one of the limitation. Second is, these are less chemically stable. Chemically stable means like we cannot use these for the quite harsh application. Quite harsh application means the pH less than 1 or pH less than greater than 13. So for the normal application, the stability of this membrane is from pH 2 to 12. That is the stability range of in which we can operate this membrane. So quite harsh acids or concentrated acid, that cannot be dealt with this membrane. Otherwise, most of the leachates or the wastewater stream, that can be recovered using this forward osmosis technology. Then the last or most important challenge is which the research community is facing, that is recovery of draw solution, because that requires quite some energy to recover the draw solution. And generally now, whatsoever application have come across, that are without the generation of the draw solution. So you have to design an application in such a way that you need not to go for the draw solution recovery. That is the simplest approach people are adopting. Even I can tell you in India, like uh, how people are doing it. For example, you have industrial waste you want to treat, and you want to concentrate it further, the industrial waste. You make a concentrated solution of fertilizers as a draw solution. That will be highly concentrated fertilizer solution, which will be having a mixture of NPK, and use the fertilizer solution as a draw solution. And what happen will, over a time, the feed will get concentrated and the draw solution will get diluted. So you will extract water from contaminated feed to draw solution, and that diluted draw solution, which is the fertilizer solution, that can be used for agriculture purpose. And this is not a hypothetical scenario. This is a implemented research which the plants are established in Gujarat, and those plants are working in Vadodara, Bhavnagar, and quite many areas in Gujarat, based on which are using RO wastewater as a feed and the fertilizer solution as a draw solution to supply the fertilizer solution for fields. Basically, that is the application of forward osmosis that I have seen in India. And till now, if anybody have a doubt, otherwise I will continue to my the work that we have done at IIT Ropar for forward osmosis. I would be happy to take the questions in the fundamental concepts of forward osmosis now.
So kindly elaborate second point. FO membranes are less chemically stable, so application with strong chemicals are limited. Strong chemicals means
Strong chemicals means the chemicals which are having the pH less than 1 pH and greater than 13 pH. Those are the strong chemicals. Its operating range is from pH 2 to pH 12. That is the operating range of this membrane that it can withstand.
but our main concern is to deal with the heavy metals and inorganic ions. That can be eliminated through forward osmosis.
Yeah, that I will show you how we have tackled the problem of uranium with the any stream. Like basically, let me brief you. Let me tell you, madam, basically what happens, like you take a industrial waste. Say you have a tannery waste. So tannery waste ka pH is around 2.5 to 3. That is towards the acidic side that it can withstand. Even we go for the mine concentrates, that uranium mine solution that has a pH of 2. So most of the industrial water have the pH between 2 to 12. So that's why this technology is now withstanding in market, because quite less chemicals we have to concentrate beyond less than 1 pH. That is basically less than 1 pH means I am talking about more than 0.7 normal of H2SO4, which is quite high. So normally this application is not made for too harsh of the acids. Otherwise, any wastewater, to best of my knowledge, that can be treated with this technology for concentration purpose. You can concentrate a tannery waste, you can concentrate a STP waste, you can concentrate your in food sector also. Like in food sector, you can concentrate the coconut milk, choco, or this caffeine contents. In caffeine industry or this in coconut is quite important, because you might have seen like the thick cocoa or the milkmaid concentrates, the milk concentrates that are developed with the help of this FO only. So FO is an application which is used for concentrating of food products quite a lot, where you can extract or withdraw quite some high amount of water from the your final product.
Right, sir. Thank you, sir.
Mr.
Any
Burma,
other question in this? Yeah, yes, sir.
Mr. Burma,
Yeah, sir. Yeah.
may I ask one question? You
Yeah,
are
sure, sir.
talking about the limitation by pH value. Now, why you are not using pre-treatment of the pH? Is another question. Is there any other constraint with the technology? Some limitation?
Primarily, these are basically the low flux is those I have already told you, like chemical stability and this the low flux and the draw solution recovery. These are the prime limitations that we have looked from the literature, quite some literature. Otherwise, these are the mainly limitation that I have read from the literature.
pH, you can tackle pH problem. There is no problem. Any chemical element which will hinder the treatment and efficiency of the whole process.
So your question, I am not able to understand
No.
basically.
What I am asking, if I adopt this technology for treatment of our water for drinking
Yeah,
purposes
yeah.
from the ground and other sources, is
Yeah.
there any other limitations of chemical nature which will hinder the whole process of the treatment.
Your
Or we can treat any
the
type of.
let me tell you, the answer
Yeah.
of your question will be come in the second part of my presentation. So
Okay,
I will
okay, okay.
showcase my uranium separation part, how we have used the groundwater remediation using forward osmosis. Then your question will be clear automatically.
It's
Okay.
okay. It's
Otherwise,
okay.
I will take your question after the second part of my presentation.
No problem. Okay.
Yeah, because
Okay,
what you are asking,
I
that is
I
covered
have
in my
one
second
question,
part
Mr. Mohit.
already. Yeah, sir.
I have one question here in this
Yeah,
section.
sure, sir. You sure? Yeah.
Um, Actually, I just want to know that what are the implication of cost for the treatment of such kind of waste and also the rejects? Because what I have seen in Bombay, Mumbai, that the reverse osmosis process has been used for treating the wastewater or sewage, and they are having a very big problem of rejects. So
Yeah,
forward
rejects.
osmosis is taking up that
Yeah,
rejects.
forward osmosis is basically made for reject treatment. Let me brief you. It's quite efficient technology. I can give you the after the presentation, I can provide you some context also. Like there is a plant that I have already told in the present during my presentation also, that in Gujarat people have used this technology for the treatment of RO waste, RO reject basically. The RO reject they are treating with the help of forward osmosis, and the diluted raw solution they are supplying to the agriculture fields. That is the
Okay,
application where basically this the because
but
otherwise
but
you have to then
there must
hello.
be very high cost implications because
No.
this
Basically, let me
technology is
tell you,
very.
this is quite, sir, let me brief you. So this is quite advanced technology. Right now, we have a limitation of membrane manufacturers also. Like n number of people, when the RO has come, let me tell you, RO is not a recent application which has come just now. RO is a quite old technology. But when initially it has come, so the cost of one membrane was around 2 lakh, 2.5 lakh also. It was too high. But now, when the demand is there, the cost automatically, the production takes care, and now you can have RO membrane a cost of 2000 rupees also. You, but that is also there. If the application will develop for photosmosis, then the cost of membrane right now people have to procure the membrane from US. When there is a cost or there is a demand of FO membrane, then definitely people will develop this membrane in India also. Right now in India, people are doing research and they are making the membrane at the lab scale. Just like we are also making this membrane on the lab scale scenario. But when there will be the demand in the industry, then definitely this thing will take care, and the cost of, if we functionally look in the material chemistry of FO membrane, that is not more different than the RO membrane. Right now, due to less demand, its cost is quite high. But if people are now started making it's not like I am talking about a rocket science type of technology. It is being used, and there are industries in India which are using FO for concentration, and some are basically importing the membrane from US. If the system is not cost effective, why a person will invest quite some amount of money to import a membrane from US and install a plant? That is my point. So basically, the answer of your question is it will take time, I know, to implement the technology on field scale or in the. This is the approach I am basically showcasing how this
Thank you,
technology. This is
thank you,
more
Dr.
towards
Mohit.
the awareness lecture. Basically, I'm not
Thank you.
selling my technology, or I'm not saying basically you take my technology, I'm providing a solution. I am a research guy. I'm just showcasing that this type of technology exists and these are the possible application of this technology.
Okay, thank you very much. The last one is that basically the rejects. I just want to know. I'm very curious to know that the quantity of the rejects from kind of wastewater, that is maybe a sewage, It will be too
Sir,
high or too
basically,
less?
yeah. Basically, let me tell you, one of research I am doing in IIT Roper, that we have made the uranium mine solution in, which is like, you might be aware of Jadugaida in Bihar is a uranium minery where the uranium is extracted from the ore and they process it through the chemical method. So we are using forward osmosis to recover the uranium from the leachate. And you will be surprised to know that at the end of the experiment, we have processed the leachate in such a way that only the salts remains. It's too highly concentrated. The solid precipitates are visible, and we can achieve the reject up to 98% in the feed solution. Up to 98% you can concentrate. Even after 98%, the membrane was performing good, but our setup was in such a way that it was not able to suck water, but we membrane was performing at that time also. That is the extent up to which this FO membrane can operate. Even in case of you have a STP sludge. So I have seen some literature articles basically which can concentrate to the solidified sludge using the forward osmosis without fouling the membrane also.
Mohit, can I speak one question? I'm Ishwar
Yeah,
Chand
sure, sir.
Jain
So my
from
goal was
Rajasthan.
when we do the forward, when we have my projects, the quantity of the rejects which are coming through the when we do the forward and osmosis, the quantity. I'm not asking
So
that how much,
that you have to
how can, yeah, please.
basically the amount of reject will be based on the cycle. Like you design a cycle in such a way that you get 2% reject only from the output. You can
Hmm.
design the cycle in such a way that I'm telling you, because uh, you have to provide the area of membrane in such a way that all of the water pass through the membrane and the amount of reject that is quite less. So that is basically the design process. How much output generally in case of uh, when we go for some tent ka RO or some house based application that has quite high reject, like the amount of water that you are extracting from the RO, that is less than half of what is being reject in RO. And but when you go for some commercial RO with the high pumps or some bigger RO system, that is a community scale RO, in that case you get less reject, like 20% reject. Up to 80% you can y- get as a permeate. But in case of FO, the reject is you can go up to the 2% of reject. That is my point.
Okay, thank you, thank you. Please continue.
Yeah.
Sir, can it be used in the industrial waste, textile industrial waste?
Yeah, definitely, sir. Textile industrial waste, it can be used quite easily.
Like Balotra, Jodhpur, Pali, they are very, very prone area for textile, and NGT again and again closes the industries. Can you give me some details of this, how it can be used in textile industries?
Yeah, I can provide you some literatures based on the how it can be used for the treatment of concentration of industrial wastewater.
Textile especially. Textile,
Ha,
the
textile
pH is
especially.
around 2.5 and this
Yeah,
color
yeah.
is
I know, sir.
also there.
Textile waste.
So
Yeah, even it can. I have seen literature during my literature survey going for tanneries. Tanneries has around 2 pH. So in
okay,
tannery it was working also.
okay, sir. My
Hello. Hello.
Hello, Jain sir, your voice is not coming.
Yeah, sir, I
Jain
am
sir,
not able to hear you. Your question was in between actually. Hello.
there may be some technical error in the side of IC Jain sir. Probably there's some connectivity issue. So I think
Might be.
Mr. Verma, you can proceed with some this other part of your presentation.
Yeah, sure, sir. Any other question, or I shall continue the rest of the presentation? So basically, uh, this is the lab work that we have done at IIT Ropar. So this is basically we have used the uranium mitigation using the forward osmosis. What we have done here. And so let me tell you. So based on the CGWB report, we identified some pockets in Punjab that I have highlighted in northeast, central part, and southwest area. And in these pockets, the concentration of uranium was more than WHO drinking water limit. And at the red points, which you are able to see here, here and here, the concentration, there is a one red point here also, which is not visible at this scale. But here the concentration is around 160. So which is quite high and alarming. So generally what we do, first we in lab scale when we are designing any technology, so we use the approach called hydrogeochemical tools. So based on the chemistry and the results that we have, we design what is the system of the groundwater. So based on the possible cations and anion, we decides which type of chemistry is dominating in the area. So based on that part, we come to know southwest region have quite high TDS and the composition is different, whereas central and northeast have the TDS less than 500. And the solution basically which is dominating here in this area are sodium and bicarbonates that are more dominating in the groundwater. So our the main composition that we have to focus or the main cation and ion present in groundwater are sodium and bicarbonates if we are talking about the technologies development of the northeast area and central areas. And in this exercise we have focused primarily on the low TDS because you might be aware of there was a decision by NGT to ban RO for the areas where the TDS is less than 500 milligram. Because of the high waste or high reject of RO, they say the RO should not be used. But it's not only the TDS is the governing factor, as we know. Based on this report, the uranium concentration was quite high, though in this area the TDS was less than 500. That's why we have used this as a research problem for my work to tackle the problem of this uranium in the low TDS scenario. So this is the methodology that we have adopted for after the finalization of the background solution, which represents the field groundwater, that is 1 millimolar of sodium bicarbonate that we have chosen based on the data analysis using the hydrogeochemical tools. So, and we have used a draw solution called sodium sulfate. Why we opt for sodium sulfate? Because using nanofiltration, we can extract water, pure water from the sodium sulfate quite easily. We have the nanofiltration facility available at our lab. So that's why we went for the sodium sulfate as a draw solution to see the how the mechanism happens. So this is the lab-based setup that we have used. So this is fully automated setup that I have developed that has some data logging, so which can continuously monitor the parameters, experimental parameter like temperature, pH, TDS, and the weight of draw solution that we can record in computer. And this is a test cell where we install the membrane, the FO membrane. And these are the flow meter and pressure gauge used for monitoring the external parameters. And this left side is the feed solution, basically, that will be recirculated at zero pressure, almost 0.1 pressure we recirculated. So it is a pressureless technology. And this is a draw solution. Over period of time, the volume of feed will reduce and the draw solution will increase. That is typical forward osmosis. So that I am showcasing here as a illustration also, that this is our diaphragm pump for recirculation, and feed will decrease over time and the draw solution will increase over period of time. And we have used a speciation modeling tool called Flixi that is basically used for designing the experiments, how to understand how basically uranium is behaving when we are trying to mitigate it using the forward osmosis membrane. And the analysis of uranium that we have concentrated or in permeate samples, feed solution, draw solution, that the analysis we have done using uranium analyzer that we have at IIT Open and ICPMS facility at Department of Water Supply Sanitation, Punjab. Mohali. And after that, basically, let me tell you. Now here comes some technical part. So I will keep my speed slow so you understand. So first of all, to understand how basically it's not like we have a uranium in a water and we pass it through the membrane and we are able to extract the uranium, that is all. So we are probing into how the scientific mechanism, how it is behaving, what are the forms of uranium that is in water. So generally, we have a carbonate system. So this is the aqueous speciation of uranium that is in C plot. So based on different pH of groundwater, in the presence of carbonates, it will make certain complexes like uranyl carbonate, uranyl tris carbonate, uranyl bis carbonate, aqueous uranyl carbonate. So these all are like the chemical species of uranium, which will be dominated at various pH. And how it is why it is important, because based on the presence of other co-ions like carbonates, if calcium is present, then the species will change, and the chemical nature of this species is entirely different. A calcium uranyl species will behave different with the membrane, and whereas the uranyl carbonate will behave differently with the membrane. Similarly, in acidic pH, it will be having dioxouranyl UO2 plus. So it will have different properties and the behavior with the membrane will be different. So for that, what we do, we take a background solution like sodium bicarbonate solution we have taken, and we do some pH adjustments. So we make the solution, feed solution at different pH from pH 4 to 10, from acidic pH to alkaline pH. We make different type of solutions, and then we run our experiment and we concentrate the uranium and we see how much concentration of uranium we are getting in the draw solution that we observe. So this plot, C plot, the blue line which is visible here. So as you can see, it has some dip around 5.5 pH. So this is 5.5 pH. So the uranium rejection is quite less or least at this 5.5 pH. Whereas we have high uranium rejection in acidic pH also and in alkaline pH also. Why it's so? That is quite important to understand to design the process. If we are designing a mitigation process, we have to understand why this is happening and what is the consequences of this. So that is quite important. So based on this speciation, we have calculated the net charge on uranyl species. How overall the charge happens on uranium species, that we have calculated during this diagram. And my membrane will also, basically what happens due to protonation and deprotonation of the surface of membrane, it will have a specific charge based on the pH of solution. So in a certain pH range, a membrane will be having negative charge, and whereas in certain pH range, a membrane will be having a positive charge. So there will be an in-between pH where the membrane will be having zero charge. That is called isoelectric point. So when the net charge on membrane will be zero. So basically that happens when we transit the pH from acidic to basic side. So there will be, when no protonation or deprotonation of surface will be happening. So that is called isoelectric point. So to evaluate this, the isoelectric point or the zeta potential on membrane, we do the zeta measurement of the membrane. That itself is an experimental procedure that we have a machine to measure the zeta potential of the membrane. So as you can see, from the 2 pH to 4.65 is the isoelectric point. Here the membrane don't have a surface charge. When the pH is less than 4.65, the membrane will be having a positive zeta potential or positive surface charge. And whereas when the pH is greater than 4.65, a membrane will be having a negative surface charge. Whereas we have the uranium species also in the same trend. So it is fundamental electrostatic attraction that happens. How the contaminant is behaving, that is the electrostatic forces. So when we have the negative charge on membrane and negative charge on the uranium species, then the repulsive forces will be dominating. So both will unlike each other. And due to that, the uranium will not be able to pass through the membrane and we'll get quite high uranium rejection, which is happening in case of the alkaline pH range where we are having high uranium rejection, and in the pH acidic also 4, because here we are having positive uranium species and the charge on membrane is also positive. So due to positive are same, we are getting the quite high membrane rejection. But near to 5.5 pH, what is happening? We have uh, the negative charge on membrane, whereas we have the positive and neutral charge on uranium, because now the forces are opposite. Electrostatic attractive forces are dominating at 5.5 pH. So uranium is attaching and it is able to pass through the membrane. So we can see uranium was depositing on the membrane also, and quite high uranium was passing through the membrane also at pH 5.5 scenario. So pH 5.5, the rejection will be less for this forward osmosis. Otherwise, for less rest of the system, uranium rejection was quite high. And this is the electrical conductivity of feed and raw solution. As you can see, these blue are the initial when we start the experiment, and this the black are the final. So for the feed also, for the draw also, we are electrical conductivity is increasing. The means of electrical conductivity is increasing. We are able to concentrate the solids in the feed solution, and we are able to extract the water out, which is a typical fundamental concept of forward osmosis. And this is a water flux that is around 6.5 liter per meter square per hour. Basically, like if I have a membrane of 1 meter square size, in 1 hour I can get 6 to 6.5 liter of water, and that is same because due to this pH it is not changing, and almost same water flux we are getting in all scenario. So if water flux is not changing throughout the pH, it means there is no chemical degradation happening in the membrane, and membrane is stable in the operational range of 4 to 10, which is the significant or quite dominating for the groundwater perspective. In groundwaters, we generally get 8.5, 7, sometime 8 also, sometimes 6.5 also. That is basically, as per IS code, 6.5 to 8.5 is the groundwater range. But generally, for the experimental aspects, we consider a broader range to be more precise from 4 to 10 for this purpose. And this is basically the continuation of the previous slide, where using the schematics, I have shown how this contaminant is behaving. Like this is at pH 5.5 scenario. Like at pH 5.5, this neutral urinal species and positive charge are attracted by this negative charge surface. So basically, it will allow them to pass also, and it will absorb on the surface of the membrane also at 5.5. Whereas if you take the case of the pH 10, which is highly alkaline pH, so there the urinal species is having tetravalent negative charge, which is quite high negative charge on the uranium species. And my membrane is also negative charge. So due to these repulsive forces, it will not allow uranium to pass through the membrane, because charge-based forces are so high between membrane and uranium. So uh, it is almost negligible uranium is passing through the membrane at alkaline pH. And when we take the case of neutral pH, like pH 7, so there we have a mixed scenario. Like we have the monovalent negative charge species and bivalent negatively charged species also. So these are repelled also, and some are getting absorbed on the membrane surface also. So it is basically an in-between scenario, like so in between 5.5 to 10, if you say. So, but overall the rejection of the uranium at pH 7 is quite high, greater than 95%. So this is basically atomic force microscopy results. This I will not be covering much. Uh, And that after that, what we do, that is the first parameter, that is pH. After pH, to design a process, we have to see other controlling parameter also, like draw solution. So draw solution concentration is also one of the prime important factor. So we can, the performance of FO process we can optimize using the area of membrane. But if we have the limitation of area means the cost. If we want to reduce the cost of membrane, we can increase the draw solution concentration also. So that we are trying to see here. What is the fundamental inference of draw solution concentration? Higher is the draw solution concentration, higher is the osmotic pressure. Higher is the osmotic pressure, more water I can extract. So what we have performed, we have used the draw solution from 0.5 molar to 2 molar. That much of difference we have checked. And see, from when we have used 0.5 molar of draw solution, 1 meter square of my membrane was able to treat around 6.5 liter of the water in 1 hour. When I have increased it to 2, then it is around to more than 12, double, more than double I am able to get water flux at the high draw solution concentration. But draw solution concentration is one factor. Like, we can further go for high concentration. That you might be thinking that if it is so, we can increase quite high concentration, but that has a limitation of solubility also. We cannot go beyond solubility. Then the precipitation will start occurring in the solutions. That is one the limitation. Second thing is, uh, you can go high draw solution concentration, but this curve is not linear. After a time, this will be trying to plateau. So we have to optimize the draw solution concentration. It's not like that increasing the draw solution concentration, you can, like here we are increasing it linearly, but my results are not increasing in the linear fashion. Like from 0.5 to 2, we have increased the draw solution concentration by 4 times, but my flux has increased to only 2 times. So based on the economics aspects and the design, we have to optimize the process. Where we'll be getting the maximum output with least investment, that we have to optimize during these experiments. So, and this rejection also, basically what happens, there is a concept called reverse solute flux. So no membrane in the world is totally diffusion based membrane. Every membrane will be having a reverse solute flux. What is reverse solute flux? That is the one of the terminology being used in forward osmosis. That when you are performing forward osmosis, a small amount of, very small amount of ions from draw solution will also try to bypass to the feed side. That is reverse solute flux. So what is the impact of reverse solute flux? So it will basically create a barrier for your uranium. It will try to shield the charge on the membrane, the reverse solute flux. And when the charge on the membrane will be shielded, then the rejection of membrane will get reduced. So as you can see, initially at lesser draw solution concentration, we are getting 95% rejection. But when we have increased the draw solution to this 1.5 or 2 times, then it has reduced by 92%. 3% reduction has been there. So that is primarily due to this reverse solute flux. That is one of the important factor that we have to consider while designing the process. And after that, there are other factors also, that is basically like co-ions. So what we do generally, like we initially went for one background solution, sodium bicarbonate system. That is a typical design process. In that we add the synthetic uranium, but that is not the case always. Then to see the mechanism how it is behaving, we go for other co-solutes also. Like one by one we add the other co-solutes. Like we add calcium first, then we'll add magnesium first to see what are the effects on the membrane system of these contaminants. Then we'll add nitrate, sulfate, and in the last we'll add all mix to understand how the uranium rejection is behaving in the presence of mixed scenario. Once we have understood the mechanism, how in the presence of various co-ions, our membrane is behaving, or which are responsible for higher uranium rejection or which are responsible for lesser uranium rejection in the membrane, then after that we are able to segregate the mix, because groundwater scenario is a mixed scenario. It will be having all type of co-ions and other metals also. So to see how what type of membrane performance we are getting with the groundwater scenario, so we have to see individual co-ions. That is experimental design that we do in the laboratory. Individually, we see how the contaminant is behaving in the presence of various co-ions. Then after that, after understanding the basic single co-ion effect, then we go for the mixed scenario, and after that we are able to see how the performance is behaving for a typical groundwater scenario of one area. Then we repeat the process for the other areas also to optimize the scenario. So this is how we can design a membrane process for the groundwater remediation. This is a lab-based approach. After that, the next part comes the scaling. How this lab-based model, once we have developed, we have optimized the membrane performance, we have optimized the draw solution concentration, we have seen all effects of co-ions also. After that, the next step is to pilot. Then we have to optimize how much water we need to treat per hour of the to supply to the public. Based on that, we take a call that how much is will be the feed solution, what is the concentration, and how much will be the reject. We have to just like sir was asking initially, how much you want to optimize it. If I want to reduce the my reject by just 2%, then what will be the size of membrane, what will be the duration of the operation, what will be the rate of filtration, what will be the amount of draw solution. That all comes in the scaling and plant design aspects. And these are the final conclusions of my presentation, that FO technology was efficient in uranium removal as a function of its water chemistry, because the chemistry that exists in the Punjab scenario, that favors alkaline range, and we have the pH of groundwater in ambient 8.5 pH, where we are able to concentrate uranium in feed, and membrane is performing quite high, with high uranium rejection in that particular pH range. And this is the finding, like uranium rejection is influenced by pH, that I have already explained. And in acidic pH, when we are having 5.5 scenario, then this absorption on the membrane of urinal species is dominating. Whereas in basic range, we are the removal mechanism is more governed by the charge-based repulsion forces. And the reverse solute flux has the negative impact that I have already told you, that if the reverse solute flux increases due to concentration of draw solute, then the uranium rejection will go down. And we have done this on Ludhiana, Bathinda, and 2-3 areas more. This Talwada also, and we are able to achieve quite good results, less than WHO drinking water limit. And uh, lastly, I would like to thank the Awadh Water Quality Soil Assessment Domain to provide under the DST and National Mission of Interdisciplinary Cyber Physical Systems (NMICPS) for funding this research. And I would like to thank the Department of Water Supply Sanitation, Punjab, Mohali, for extending their support in the ICPMS also. And I would like to thank my department, Punjab Water Supply Sewerage Board, for the field sample that they have collected from the actual groundwater in Punjab at different location and provided to IIT Ropar for the development of this work. And this work was published in Chemosphere Journal also, that I forgot to include. And that is all from my side, guys. And I can take questions. Thank you. Thanks a lot.
Thank you very much, Engineer Mohit Verma, for your scholarly presentation. Indeed, it is a very presentation full of knowledge. And I'm thankful for the participants also, Dr. Sanjeev Agarwal, Dr. Dinesh Sant, Mr. Shashan Jain, and Ms. Manju also. but it would have been better to if they introduce themselves before any question. Anyway, now I request any other participants who are interested to put some clear some doubt from Mr. Verma. So now the session is open to you all to clear your doubt from Mr. Verma.
I can see my slides here. If somebody wants to ask from slide, they can ask from the slides also. Any questions, please?
Is
Hello?
this technique is viable? Is it cost viable technique?
Sir,
Mr. Shobhanaranjan
we,
Ganguli is asking if the technology is cost viable or not.
sir,
viable or
basically, let me tell you, sir. So the work that I have done on this technology, that is more about the technical feasibility, whether this technology will be able to remove uranium from the contaminated groundwater of Punjab, that we have explored. So the cost effective analysis was the future aspect of this work that we have to take up. So that we have not done yet. So that we have to do the plant design first with the theoretical calculation that we have to take the all aspects of the operation maintenance, membrane cost also, and the power required for RO also, that we are planning to take it in future to compare the cost of this forward osmosis with the nanofiltration and reverse osmosis for the same type of the feed water. What is the amount of reject we are getting, and how it will be the cost effective, or what will be the possibility to scale it up. That is the future scope, sir.
But now, after cleaning of the material, where it will be discharged, it will be discharged into the natural stream or water or field. Then leachate will come. Then what is
No,
your
sir.
planning?
Basically, let me tell you, the amount of concentration that we can achieve using this is near to supercrystallization. So, the basically the if we are treating 100 liter of water initially, I am giving just an example, vague example. If you are treating a initial feed of 100 liter, then your output which is left reject is less than 2 liter, and that will be quite like a sludge, quite thick sludge. That is, with with no time, it will solidify to a salt. It is solid salt that we get in the last. So I have some snapshots also, but right now I'm at my home. But I could show you those snapshots also. Otherwise, I was planning to include in my slide. That will be more fascinating, and that will look nice to see how the powder form we get after the processing of
Okay,
this.
but where these
Yeah.
solids will be where these solids will be discharged?
No, sir. Basically, but
If you discharge
sir,
into the
let me tell you, sir, that what you are asking me, that is a reject management. So uranium will be there
yes,
as a radioactive element. So uranium powder
yes,
or uranium solids you cannot discharge anywhere, anytime. So generally,
yes,
Department of Water Supply Sanitation has done a pilot project based on adsorption also, that has got sanction from BARC. So basically that the residue, final residue you have to deposit for the radioactive recovery, that I was
yes,
aware of. So that has to we have to deposit to the BARC if we were planning to install a plant based on FO. So the final product we have to get the sanction from BARC and we have to deposit there. So which they will be using for some resource recovery, because here the waste is quite valuable. It's not like a waste. It's basically a resource which can be used for the further energy generation or other purpose also.
okay, okay, okay. And now I got my point. Thank you. Thank you.
Yeah, thank you. Thank you for your
Uh,
quite deep
Uh,
and fundamental question.
Okay.
yeah,
Dr. Verma, Dr.
okay.
Verma,
Sir,
sir,
yeah, sir.
May I ask one question?
Yeah, sure. Can you please
Yeah,
introduce
I am
yourself also, sir?
Dr.
That will
Dinesh
be good for
Chan.
me also.
Yeah, I am
Sir,
Dr. Dinesh Chan. I am a national WAS
sir,
expert. Now, my question,
sir,
maybe
sir.
technology, what you have presented is very good, congratulations to you. But now we are searching a solution in a rural area. Now, my question, adopting this technology in a rural water supply schemes, keeping in view the externality of the operating condition required and financial support, whether we can support it. As you know, JJM says that it will be publicly, means a community will operate the schemes. So whether they can afford,
Yeah,
or
yeah.
what type of
Yeah,
your views
sir.
on this?
Let me tell you, you have
Yeah,
asked me a quite excellent and quite a fundamental question, which we have covered also initially
yeah,
during this presentation. Let me brief you. So there are a number of technology. Everybody will say my technology is best. I am also a designer, membrane-based guy. I will say my membrane is the best. Everyone say generally that this technology is best, that technology is best. But
yeah,
there are certain parameters that we have to see. One is the initial investment, one is the reoccurring, one is the life of the material. So for example, if you take an adsorbent basically have a shelf life. So after some time the adsorbent will be exhausted, so you have to replace
replace,
the
yes,
adsorbent entirely. For
yeah,
example, RO membrane has a shelf life. After some membrane time it will foul, and you have to
yeah,
replace the membrane again. Like
yeah,
generally, if you have designed a RO system quite good, then
yeah.
the operational time is around. People claim that it is 5 year, but I have not seen any RO 5 year type scenario.
Maybe two
Generally,
years to 3 years
2 to 3
maximum.
years is generally RO system will become unfunctional.
Yeah, yeah,
But that is the beauty of forward osmosis, that it is a pressureless system,
yeah,
that its life is quite high.
yeah.
But we have to evaluate it. People are doing the research from years to years. I have scientific literature that people have operated continuously up to years, like 3 years, 4 years continuously, and
Mm,
no fouling has happened on the membrane, that are there. And secondly, if you have installed the system, so it is maintenance free system. The power requirement is quite less. So that is the beauty of this forward osmosis. Second thing is the application in the community side. See,
yeah,
we cannot force any technology everywhere. Like I have designed a technology for, say, Punjab, that
yeah,
might will not be suitable for Maharashtra, that might will not suitable for Andhra.
yeah, yeah.
So based on the hydrogeochemistry, what I have showcased, what is the process to design a mitigation strategy. This time I have used a forward osmosis as a tool. Forward
Yeah.
osmosis is a tool basically. Overall, what I have presented, that is how a technology can be designed at a lab scale level. That is the purpose of this presentation. It is not about proving about the benefit of forward osmosis.
No, no.
We have
What I
worked
was
with.
actually searching,
Let,
you have
let me complete, sir.
advantage both way.
So,
You
sir,
are
sir,
working as
sir.
a
Let me.
scholar, research scholar, and as well as in a department. So you have
Yeah,
greater
yeah,
opportunity to say,
yeah,
yes,
yeah. I
it
know.
can be adopted.
Yeah. I am telling you,
Yeah,
basically, I have during my PhD, I have worked on various technologies. Like FO is the one of the technology.
yeah,
Secondly, after that, we have worked on nanofiltration also, and we
yeah,
have worked on ultrafiltration also,
yeah.
and we have worked on microfiltration also. Even I can remove uranium using microfiltration membrane also, which
Okay.
is uh, one can ask me how a microfiltration membrane, which can remove only suspended particles, can
Yeah.
remove a uranium, which is quite
Mm-hmm.
small in size. How it is
Mm-hmm.
possible to, but the mechanism is different. The
Mm-hmm.
way the microfiltration membrane, we just coat the membrane with some super nanoparticle, like we have made in laboratory, and that will be used as an adsorbent. So basically, it's a filtration cum adsorption type of technology. So based on the hydrogeochemistry of a region or the properties of the uranium characteristics, groundwater properties, we have to come up what type of technology we have to use. Considering it can be adsorption, cum membrane, it can be a totally membrane, it can be RO, it can be a FO also. So
Yeah.
our purpose is to showcase how this mitigation technology, if some guy comes to you tomorrow
Yeah.
that I
Yeah.
have a black box, technology is not a black box. First of all, technology
Yeah.
is fundamental basically. So
Mm.
how that technology works, that is the my purpose of this presentation today. This is forward osmosis. Next time it will be microfiltration come adsorption also. So how a specific technology can be used for your mitigation purpose, that what we do at the IIT Ropar, sir.
Yeah. Thank you very much.
And
Very good.
taking it to the field, that needs the support from department, from the administrators. Quite some support is needed. You might be aware of that
Hello.
Department of Water Supply Sanitation has installed adsorption, but adsorption as for arsenic removal, that is also one type of technology. But
Yeah.
every technology has their pro and con.
Yeah.
In Rajasthan, ultrafiltration based technologies have been implemented and that are quite successful
Yeah.
for removal of the TDS, organic matter, and even trace elements also can be removed from that ultrafiltration membrane. So different type of technologies are being used in India based on the hydrogeochemistry and other aspects, sir.
So
Okay.
thank you,
Very good.
Mr.
Yes.
for your question and beautiful explanation by Engineer Mohit Verma. I have seen Dr. P. Sivram raising his hand to put a question.
Yes, sir.
Dr. P. Sivram, there?
Yes, sir, I'm there.
Yes.
Good evening, Mr. Verma. My name is Dr.
Yeah, sir.
Sivaram.
Sir.
I am a national
Yeah,
laws
yeah, sure.
expert and former
Yeah, yeah.
professor and head of National Institute of Rural Development and Panchayat Raj, Hyderabad. My
Yeah,
question
yeah.
is, not my first my question. First, I must congratulate you and a beautiful presentation. I really enjoyed your presentation. That's coming to only one
Thank you, sir.
question. Yeah, very simple question, and the lab to land concept. And you made it in the lab. What about to land? That is another point I wanted to mention. And
Yeah, yeah.
what are
That is quite
what are,
important, sir.
what are the policy options? Are you influencing the government to adopt this technology? Like one example, I'll tell you, Batinda. Batinda is the capital of cancer. And by consuming
Yeah,
the
yeah.
water, many people, many farmers, many people are suffering from cancer.
Yeah,
And
yeah.
this technology, whether really useful to the community, and you can say that, yes, what about influencing the government and what are the policy options? Please throw some light on this. Thank you so much.
Sir, the question that you have asked me on the name of a simple question, that is the most difficult question, first of all. Huh? So basically, these are, yeah, you are right. Basically, we are from the research background. We work in lab and sometimes we do the pilot also. But these technologies need initiative from the government also. If there is some collaboration normally from the government, so if the project is sanctioned by the government, then these can be made. Yeah, you can work in the field, but right now whatsoever we have done, that is at the lab scale only. So that we have to see whether this will get some support in future from the government, whether it will be feasible that we have to we can say only once we do the pilot on some location in Punjab. So for that we have to do some pilot first, then only we'll be able to see. And for that we have to uh, see how is the support we get from the government and who is going to take it up, kind of.
Yeah, thank you. Thank you so much.
So another raising hand, Prakash Chandra Samar. Sir, are you there? Prakash Chandra Samar.
Yeah, sir, you are audible only, sir. Yeah, I can hear you.
One another participants want to ask you some question maybe.
Yeah, yeah,
Here's
please, sir.
Prakash
sir.
Chandra.
I am Samar. Am I audible?
Yes.
Yeah,
Yes,
yeah,
yes,
sir,
sir,
you are.
Sir, very good evening, sir. Thank you very much
Very
for
good
very
evening, sir.
nice presentation. Sir,
Sir.
sometimes back I've been to Punjab. As you are elaborating about the
Right.
Punjab, there was some, I think, iron arsenic removal plant. Like that, uranium plant should also be there. Somewhere contamination is there. So, as everybody knows that looking towards the geochemistry of the area, the rejected water should be treated before reaching to the groundwater. So every state is having some policy matter regarding the treatment of the rejection water. So what about the policy of the Punjab state for this rejection of uranium water? Generally, they are leaching water to the groundwater through constructing a pit with the filled with the pieces of the brick beds. That's it. That is the procedure I have seen in Punjab. So whether it is right or wrong, because policy should be followed in every case. So please throw some light on the state policy regarding the removal of the uranium.
So right now, basically, it's a quite important question that you have asked, but
Sir.
unfortunately, about this policy matter, I am not much aware of, because whatsoever we have done, that is from the technical aspects to develop a technology, and how this is being, because right now we have arsenic plants in Punjab, but uranium plants might be government will take up in future, and for that they will make some policy also. So because it's quite some time I am in from out from this the departmental side, so I can address the questions more from the technical aspects, like about how this forward osmosis or this technology we have developed, and that is useful or
Sir,
that it
actually,
can
I want
perform.
to note that whether they are actually not following any procedure. They are rejected water. They are spreading out generally. In formality, they have constructed some pit and some brick pieces are there. That's all. So whether it is right or wrong, because uranium as well as arsenic is very much injurious to health. Everybody knows. So there must
Yeah,
be
yeah,
they should follow some strict policy. Yeah.
Sir, can I add something, if you allow?
yeah, madam. Sure, madam.
Sir, good evening, Prakash sir. This is Manju from Department of Water
Oh,
Supply and
welcome, Manjuji,
Sanitation.
welcome.
How are you, sir?
Fine,
Sir,
fine. Yeah.
one uranium pilot project is running by our department in the area of Amritsar. As far as I have the insight, the whatever the sludge is being collected by that plant, that we need to send at the BARC, because they can only the treat uranium. We don't have any facility over here. So if I think all over India, if any of the state is going to implant the uranium removal plant, they have to collaborate with the BARC. Otherwise, they won't allow us to put that plant. This would be
So,
the
Yeah,
policy of the government. It's
yeah.
Madam
already
Manjuji,
This I have.
may I ask
Hello.
Manjuji,
Ji,
is it
ji.
right in 100% cases? They are
Yes,
rejected
sir.
water,
Yes,
they
sir.
are
Because
collecting and sending to BRC?
not they, yes, of course, because this is the mandatory and obligatory part. This is a written documentary they have to go through, because uranium, it as such is a radioactive, and we cannot leave it just like this, because whatever the plant, even if the RO we are going to use, the uranium whatever discharge through backwash, that is quite harmful, and because of the radioactive, BRC is very strict in these things. This is
Madam,
a policy of the government.
as
As
you
far as
might be remembering, I've been to Firozabad like that, and your some officers were telling in the field that it is uranium removal plant, but they were not knowing the detail about that one, and that was also not working there.
so
I was
might be
having
they are
doubt
not.
whether uranium is reported there or not, but your field officers were telling that it is a uranium removal plant. Once upon a time, it was very rich in the uranium, that particular village water. like that. But I was having doubt because that must be only a RO plant. It was not a uranium removal plant. I have never seen in the Punjab, in the field where I been.
So it is all over Punjab. It is only one pilot project is running around in the area of Amritsar in the Maja area. But might be your whatever the state you are referring, they are oblivious of these facts that we have to tie up with the BARC, and it is a very I think this is a I think you should let them know if they are not aware of this.
Okay, but I myself was having doubt. They were reporting that it is having high uranium content, but unfortunately the plant was not working like that.
Anyway, thank you
I
very much for
cannot
the
comment
all
over
Punjab
that.
conversations. I
Anyway,
have
thank
seen
you.
our advisors, Sir has joined, Mohammad Ishfaq sir. He's the advisor of SPM Nivas. I will insist that Sir should speak out something on this webinar, please. Sir, can you hear me, sir?
Yeah, thank you. First of all, let me extend my thanks to.
Good evening, sir.
Good evening.
Good evening, sir.
Mr. Boy, for a wonderful presentation. So, due to my previous engagement, I was not able to listen to the complete lecture, but I will definitely try to listen to the recording. And this is very, very important topic, management of the uranium in the drinking water. And in Punjab also, we are facing uranium, arsenic contamination, fluoride contamination. So there are many issues. Regarding state policy, as some question was asked in the policy matter. So in Punjab, if you see the history timeline, initially in Punjab, we never went for any removal plant. As somebody was saying, most of them ROs were installed. So there was one foundation, which was Nandi Foundation. I'm telling you the historical perspective of the RO plants. So Nandi Foundation was an NGO. So they arranged some fund from the sources, from maybe some donations. Then they installed few of the RO plants in the villages. Those RO plants were not supposed to be treating any contaminant. They were basically a secondary source of water supply, because water supply in all the villages of the Bathinda area, for example, not Firozpur, but Bathinda area is based on the canal water. But sometimes there is a canal closure, so there is disruption in the water supply due to non-availability of raw water. So during those times, those RO plants were constructed, and those RO plants were quite popular. Then those RO plants were using the shallow tubal water, which were having uranium also, which in some cases are having other contaminants also in some cases. So at that time, the protocol followed by the department was that whenever there is a water which is having uranium, so they used to dig 2 tube wells, one to extract the groundwater, and second was to again you can say discharge the reject water in the same aquifer. The theory was that since we are withdrawing from the same aquifer, so we are adding again, we are not adding it to the pollution load of the aquifer, because that uranium is already existing in the aquifer. Same strategy was even used in the USA also at that time, because at that time the focus of the government was to provide people a uranium-free water, and then they said the quantity of extraction of groundwater on such RO plant is very, very low, so it will not change the composition of the aquifer water, because if you are adding the reject water which is having a high concentration of uranium to the aquifer. So that theory went on. Later on, many people raised questions on this policy. They said this is not environmentally safe. Ultimately, you are extracting water, but you are adding the contaminants again to the aquifer. This is not a good practice. So that's why Punjab went for uranium removal plants, arsenic removal plants. So we use the technology developed by Dr. Pradeep from IIT Madras for arsenic removal. Now the pilot regarding uranium removal has also been installed. But right now, technology for the removal of uranium has not been vetted by Government of India. When I was mission director, we sent a reference to the Government of India to vet the technology so that we can replicate it on large scale. In the meantime, Punjab went for the long-term solutions. So wherever we are facing contaminants, maybe on account of various contaminants, fluoride, uranium, arsenic, now we have gone there for a megawatt supply scheme, which are covering 100 to 150 villages. For example, in Firozpur area, during my tenure, we started 2 schemes, I think there. The megawatt supply scheme, where the purpose was to fetch water from a nearby canal, which is a perennial canal, then treat that water and supply the water to all the villages where piped water supply network is already available, overhead tank is already available. So this additional layer of the system, bulk water supply, the plant will supply water to the overhead tank at the village level from the overhead, and the tubewell which was functioning there will not be used for supplying water. But again, then there was a demand from the villagers, so we went for the conjunctive use also. So then they said, in case you want to use water for non-drinking purposes, because the cost of groundwater is very high, so then you can use some water with the consent of the community and a lot of IC activity, that in one shift you can supply water from the tubewell, and then tell the people that they should use this water for the other purposes, not for the human consumption. So that theory was going on. But right now, Punjab has taken a strategy that they will replace all these solutions, because all are short-term solution, with the megawatt supply scheme, and we will take the water from the canal sources. The problem will remain only few pockets which are very sparsely located, where megawatt supply scheme is not technically feasible. There even we have went to the extent of distributing the home-based arsenic removal plants also. I think when I was the district magistrate of Gurdaspur, at that time we distributed arsenic removal plants to each and every household. So water contamination on account of uranium, arsenic, fluoride is high on the agenda of the state government, and Punjab is perhaps the only state which was testing all the parameters. Why it happened? Because when I think in the year 2000 or late 90s, there were a lot of incidents of cancer in the Malwa belt of the Punjab. So people went for testing of the hair samples of the diseased patients who were cancer patients, and they found a very high level of uranium in their hair content. From there, the suspicion rose that probably they might have the cancer on account of high uranium. But so far, no medical study has established direct correlation. In fact, I am telling you, this uranium which we are finding in the water is not radioactive. It's of geogenic reason. It can be treated as a heavy metal. It is not radioactive material. So you cannot produce a nuclear bomb from this uranium. It's not radioactive. So the scenario now, after the Punjab went for the comprehensive testing, many states are carrying out the comprehensive testing. Even in Punjab also, there was no testing of the urban water supply scheme. So when I took the charge as the CEO sewerage board, Mr. Mohit was there. Then we promoted the testing of the urban tubewells also. Now when we tested urban tubewells, we have found these contaminants in the urban water supply also. That's why now at Ludhiana, at Amritsar, at Patiala, at Jalandhar, all the mega towns now are being shifted to the surface water supply scheme. So this is the policy of the state government in the Punjab, that we are trying to find both long-term and short-term solutions, and try to find the technologies which are environmentally safe also and which are sustainable also. Regarding today's lecture or the inputs given by the Mohit, so I will request the Mohit that please send us a complete note to Mr. Sekia, and then we will examine your note in-house, and then we will bring it to the notice of our professor chairs also, because we have many professor chairs, and one of the professor chairs is from IIT. They are responsible for monitoring the water quality issues. So we will share your note with them also and have some discussion. And in case everybody is satisfied that the solution proposed by you is a good solution, then we can definitely provide you some assistance after consulting the government at the ministry level, that how we can support this project. We can definitely consider thinking, extending some help to IIT Ropar to carry out further, to install some pilot projects, to carry out further evaluation. But uranium and other contaminants are very, very important. We need to look into them. We need to, first of all, I have seen many chemists have joined. We need to carry out the comprehensive testing. Because if you're not testing your water for all the parameters, you will not able to find what is in the groundwater. Even in Punjab also, unfortunately, before this incident, nobody was testing the water for the heavy metals, and they were only testing the water for the basic parameters. So only that now Punjab has shifted for testing various parameters. Right now, even there are many state governments who are not testing the water for the various parameters, that too on regular basis. And the water quality scenario is also very dynamic. The concentration levels are changing from time to time. So scenario is very complex. That's why at SPM Nivas, we are encouraging a lot of discussion, a lot of debates. I hope Mr. Sekia might have noted on all the points. So all the points which various people have asked, we will try to collate all the data which we collected from today's webinar, and along with the note from Mr. Mohit, and we'll try to present this case to the Additional Secretary and MD JJM for his advice and comments. In case it was found suitable, we will definitely go ahead with that. So far with that, thank you very much. Thank you very much for your participation, Mohit. And
Thank you, sir.
good work for your research. Thank you.
Thank you very much,
Hello.
advisor. Probably
Thank
now
you.
it's clear to all regarding the policy matter and existing scenario of Punjab so far this heavy metal is concerned. So I think nobody is there to put any more question because it is
Sir,
already
can I
10:45.
speak something?
Yeah.
Yes, definitely, you can speak.
Sir, regarding this presentation that we have done, today I have presented this the note on this forward osmosis. But IIT Ropar, we have worked on various technologies like ultrafiltration also, nanofiltration also, and microfiltration also. So I have couple of solutions. It's not only one solution we have worked, and that all have different type of advantages. So if we are going for a domestic solution, some technologies are more economical or long term sustainable. So instead of proposing one technology, what we can do, we can propose 3 or 4 cases also from our side for your consideration or to send to.
But in that, Mohit, your note should come very clearly. Where do you use which technology? You should give
Yeah.
options with the
Comprehensive and where it is feasible.
selection matrix, so that which technology suitable to which area, which type of contaminants.
No, advisor, sir.
Yeah.
Sir.
Yeah.
Good evening.
Good evening, Dr.
It's a good suggestion that some technology from your institute support and then PhD Punjab come together with IIT Ropar and then have some pilot project thing to showcase technology for other states also.
Yeah.
So funding can be done by ministry.
Yes.
I think there will be no problem.
So we will try to evaluate the proposal sent by the Mohit and take the comments from one of the professor chair also. And if it is found suitable, then we will definitely push it forward. Recently, I have sent one proposal to the ministry for the approval because you see in the coastal areas, even if you are installing a surface water supply scheme, the inlet point is within the 50 or 60 kilometers from the sea. There is also incidence of high level of TDS in the water. Even if the river water, that's also hard water. So we have proposed one research project with the joint, I think, Jadavpur University. Yes, so with the Jadavpur University to carry out some feasibility study and to identify low-cost solutions in such cases. Because normally our surface water supply treatment plants don't have any equipment or any part or any component which is able to remove the dissolved solids. We are only removing the suspended solids. So we can send another proposal to the ministry, and then with the consent of the comments of the professor chair, we can definitely push forward such technology. Even we can request the government of Punjab also to sponsor one of such technology. There is no big issue. Thank you.
Thank you.
And Sumindra Rajan Ganguly, I think he has.
Thank you very much to all the participants.
Mr. Ganguly has also raised his hand.
Mr. Ganguly has already raised his question. Probably it is clear to him. Mr. Ganguly, I think actually perhaps he forgot to raise down his hand because he put some question and got his answer also.
Okay.
So congratulations to Engineer Mohit Verma.
And let me say a word of appreciation for Mohit. Mohit was working with me as an executive engineer. So there he developed the water quality monitoring protocol. And to my pleasant surprise, I have found it is still working.
Yes, sir, he is a young man, sir. We should take his brain to the JJM.
Yeah, definitely. So,
but Mohit is going to US, sir. For next week, he is flying to US.
Okay, no issue with that.
So congratulations.
My best wishes to you.
Thank you, sir.
So once again, thank you very much to all the participants. And though it is a very scholarly presentation, but I have seen that so many our these veterans took part in discussion. As many as 7 participants has raised questions, and that too of very important one. Mr. Engineer Mohit Verma said himself that these questions are very typical and very important as well. So thank you very much for your continuous support. I hope to see you once again. And I request Mr. Verma to act accordingly as our advisor sir has
I think
seen.
he can do webinar from USA also. No issue.
Yes,
Yeah.
yes, definitely, definitely.
Yeah,
We are
yeah,
looking
sir.
forward some
For
more
you,
inputs.
for USA, I'm not going permanently, sir.
Okay, okay, okay.
No, no
Sir,
problem. You can interact regularly.
sir,
We are
I
looking
am going
forward.
for just one. I am going for a
Okay,
purpose of conference only. It's not a permanent thing.
Oh,
okay, okay.
so you are
Okay.
got.
Yeah, yeah. I am here
SPM
only.
Nivas, SPM Nivas wishes a very pleasant stay at USA and a very success in your conference also. So have a safe journey and come back with some new ideas and give us some webinar so that to share your knowledge also.
Yeah,
What
yeah, sure,
you
sir.
get in USA. Thank you. Thank you very much. Now
Definitely,
we
sir.
are going to
Thank you.
close this webinar. Thank you.
Yeah.
Thank you once
Thank you.
again. Thank you very much.
Okay.
Thank
Thank
you,
you
sir.
very. Bye bye.
Bye, sir.
Bye.
Two hours.